And today we're going to begin looking at ideas within Chapter 5. Chapter 5 is interested in aspects of energy and how it relates to matter. So in today's class, we're going to begin by looking at sections 5.1, 5.2, and 5.3. Looking at a few of the different descriptions of energy, considering the first law of thermodynamics, and introducing the topic of enthalpy. For the pre-class activity, you are asked to look at ideas involving kinetic energy, potential energy, system surroundings, and extract information from the e-text to have a initial understanding that we're going to build on in class today. The way today's class is going to be run, within this video, the teaching assistant is going to help guide the discussion as we make sense and work through the different ideas. Along the way within the video, you're going to have opportunities to share ideas with your classmates and with the teaching assistant. The slides that are used within the presentation have also been provided for you here within the activity. So let's get started. So a goal at the start of Chapter 5 is to make sense of different terms and definitions. The symbols that we have for those: heat is given the symbol Q, work is W. We have potential energy and kinetic energy, PE and KE. Something called the internal energy is given the symbol E, and we can connect these ideas to temperature. So to begin to make sense of them, the kinetic energy and the temperature go together. The temperature, in fact, is a measure of the average kinetic energy of our particles of matter as they're moving through space. So when we use a thermometer, the thermometer is telling us something about the particle motion. Energy can be involved with chemical reactions. The unit of energy is called the joule. Oftentimes in a chemistry class, we're interested in kilojoules, thousands of joules. So when you see the energy, it'll probably either be joule or kg for kilojoule. So energy is involved in chemical reactions. Energy is also involved with physical changes. Melting an ice cube, turning it from a solid to a liquid, we're adding energy. Boiling water, taking it from a liquid to a gas, we're adding energy. Condensation, the phase change as we go from a gas back to a liquid, that involves removing energy. So energy is involved with chemical changes, and it can be involved with physical changes. Back to that pot of boiling water. If you raise the temperature of the water to 100 degrees Celsius, it'll begin to boil. It goes from the liquid water at 100 degrees Celsius to the gas. The gas is also at 100 degrees Celsius during this phase change. So if they're both at 100 degrees Celsius, they both have the same average kinetic energy. But what's different is the potential energy. The position of the molecules is different when we consider H2O as a liquid and H2O as a gas. Learning more about the potential energy, that's an important goal for us. To do so, we're going to investigate kinetic energy and potential energy by looking at a skater on a frictionless track. Our goal of this part of the activity, we want to make sense of the relationship amongst the position of the skater, the kinetic energy, and the potential energy. Here I show three different bar graphs. Your goal is going to be to match the bar chart to the image of the skater. So I'm going to show a little video, and along the way, talk to a classmate. Your goal, again, is to make sense of the position of the skater. What does it mean in terms of kinetic energy? What does it mean in terms of potential energy? Here's our skater. Look at the position, the motion, kinetic energy, potential energy. Okay, take a second. Check with your classmate, share ideas with the teaching assistant, match the bar chart to the image of the skater at the different positions with the data shown at the bottom. So hopefully you came up with an answer like this. We see that when the skater is far away from the ground, the potential energy is the greatest. If they're in between, we have a combination of potential energy and kinetic energy. And when they've reached the bottom, the potential energy has gone down to zero, and they are entirely kinetic energy. look at this particular image. This skater is at the bottom of the ramp, but the potential energy, it's not zero. It's still positive. Check with a classmate for this one. Why do you think in this scenario the potential energy is not at zero? An important detail is what we are calling our zero potential energy, our reference value for the potential energy. In this case, even when the skater is at the bottom of the ramp, they are still elevated. They have not reached the ground. So they would still have some potential energy even if we reach the bottom. But now in this simulation, we can change what we are calling potential energy equal to zero. We can change our reference. That's that dotted line. So in this case, if the potential energy reference of equal to zero is at the ground, there is still some potential energy at the bottom of the ramp. However, if we raise it so they match, notice now how the potential energy reaches zero. The motion of the skater is the same. We're just changing our reference value. If we raise the potential energy reference even higher, the motion is the same, but now notice sometimes the potential energy is positive and sometimes it's negative. It all depends on where our reference value is. If we were to raise it all the way to the top, now the potential energy goes to zero, and then it becomes more and more negative. It becomes smaller and smaller. So the potential energy is going to be lowest when the particles of matter are attracted to each other and they are close together. In this case, the potential energy was the lowest when the skater moved closer to the ground. There was an attraction between the two of them. As they moved closer and closer together, the potential energy went down. Potential energy is going to be the smallest when the particles of matter are attracted to each other and move closer together. However, we're going to need to know where the potential energy of zero as a reference value is set. A negative potential energy is possible given our reference value. Those ideas show up here. Potential energy has to do with the position of our particles of matter. And in a chemistry class, the most important form of potential energy is the electric potential energy. It has to do with the charges for our particles of matter. If we look within this description, the reference value of potential energy equals zero is being set for when the particles are far apart from each other. If there is an attraction and they begin to move closer together, the attraction is because the charges are different from each other, opposite charges. As they move closer together, this coming together, the potential energy is getting smaller. And because our reference value, potential energy of zero, was when they were far apart, that smaller and smaller potential energy means they become more and more negative. Now you could have the particles of matter with the same charge. If they have the same charge, as they get closer and closer together, they're going to repel each other. And in this case, the potential energy would become higher and higher, more and more positive. Now in this class, we're going to be very interested in scenarios in which the particles might be far apart, potential energy of zero, or as they move closer and closer together and become more and more negative as there's an attraction that takes place. Let's try to put this then in a chemistry context. Suppose we had two ions that are stuck together, like a sodium cation and a chloride anion. Now when they're stuck together, how would we describe the potential energy? Remember to account for our reference value for our potential energy. Check with the person next to you. Given this scenario, where would you put this combination of a sodium cation and a chloride anion when they're stuck together on our number line here? I see within this scenario, we have a positive charge and a negative charge. When they're stuck together, the potential energy has decreased as they've come together, So that would now result in a very negative potential energy, a small potential energy value. Here's another way of looking at that. So here we have a whole bunch of cations and anions far apart. As they move closer and closer together, the potential energy goes down. The potential energy becomes smaller, which means more and more negative. We can connect this to the skate park. When there was an attraction and our particles moved closer and closer together, potential energy decreased. Same thing here. When the particles of matter are stuck together, they have a lower potential energy than when they were apart. Now, if we think about that, it's going to take energy to move them apart. It's going to take energy to increase their potential energy. If we think about this as it pertains to bonding, it always takes energy to break a bond. The atoms are initially stuck together at a lower potential energy when they're bonded, and in order to separate them, we have to increase their potential energy. It's always going to take energy to separate them. And if we think about the opposite, forming a bond will always release energy. If we go from a higher to a lower potential energy, that energy then is released. Check with a classmate. What questions do you have based on the information we've been talking about thus far and what's shown on this slide? Now, we've been talking about energy and its transfer. An important detail there is to think about what type of system are we talking about. We need to be careful with our definitions within this chapter. System and surroundings. System refers to the part of the world that we're interested in studying. The surroundings is everything in the universe outside of that. So the system that we're interested in could be a beaker of water, and the surroundings would be everything in the universe outside of that. Now, different types of systems have different types of definitions. So I show here at the bottom the different definitions and three types of systems, okay? Three scenarios: a piston, a pot of boiling water, and a thermos. So take a second, check with a classmate here, try to match them up. Which one do you think represents an isolated system, a closed system, and an open system? Here would be the best answers. We have an open system, like the pot of water, where energy and matter can come and go into the pot, out of the pot. We could heat the water, and the water then goes into the air. An isolated system, where we're trying to say both the energy and the matter inside the container are not interacting with the surroundings. And finally, a closed system. In this case, energy can come and go, but not the particles of matter. The particles of matter are stuck inside the system, stuck inside the container. Now, you notice here, this is a piston, okay? So the piston is holding the matter inside, but its volume can change. Let's learn a little bit more about what that means to say energy can be exchanged when it's in a piston. The first law of thermodynamics tells us that the total energy of an isolated system is conserved. If the energy can't be added or removed, then it's going to be remaining constant. Within section 5.2, let's look at a few aspects then of the first law of thermodynamics. First one's called the internal energy. So the internal energy, given symbol E, that would be the sum of all of the kinetic energy and all of the potential energy for all of the components you have in the system. So if we're looking at these H2O molecules bouncing around, kinetic energy because they're in motion, potential energy as we think about their position relative to those of the other molecules. Now, we have this comment: we generally do not know the numerical value for the internal energy. This would be really difficult to calculate because all the particles are in motion, their positions are changing. So instead of trying to say a specific value for the internal energy, we're mainly concerned with how it changes. So delta E, which means the change in internal energy, is something we can calculate. We can ask the question, what is the final internal energy minus the initial internal energy? Oftentimes in this chapter, we're going to set up expressions like that. We're going to be interested in the final state minus the initial state. So to illustrate that, here we have some O2 molecules as a liquid. They're moving around, so they have kinetic energy. They have potential energy based on their position. What is that internal energy? I don't know. But I could measure the energy that I add in the form of heat here, which is changing the internal energy. So I'm not necessarily interested in the absolute value for the internal energy, but I'll be often interested in describing how I change it, how I either add or remove energy from the system. So I've mentioned that we can change the internal energy. Take a second. Next discussion question for you. What do you think has the higher kinetic energy, the higher potential energy, and the greater internal energy when we compare O2 solid at 31 degrees Kelvin and O2 gas at 194 degrees Kelvin? Which of these has the higher kinetic? Which of these has the higher potential? And which of these has the greater internal energy? Discuss that for me. So as I look at this, I think the O2 gas at 194 Kelvin, it has the higher kinetic energy. If I look at the thermometer, 194 K is higher than 31 K, so it has a higher kinetic energy. How about the potential energy? The potential energy is going to increase as our particles which are attracted move apart from each other. They've moved apart from each other more in the gas than in the solid. So I think that the gas has the higher potential energy. Finally, if the internal energy is a combination of the kinetic and potential, then I think the O2 gas at 194, it has to have the higher internal energy as well. So if I were to stack them up this way, O2 solid at 31 K has a lower internal energy than the O2 gas. If I was initially with the solid, I could add energy to raise the internal energy to reach the value for the gas here. If I were to do my math here of looking at the change of the final internal energy minus the initial, in this scenario, it would have a positive value because I'm going from a smaller value to a larger. When I do final minus initial, it'll be a positive value. Our change in internal energy, our delta E, it is going to be positive when energy is being added to the system. And that's what we have right here. The change in internal energy would be positive as we go from a lower initial to a higher final. So the internal energy then, that's the sum of all of the kinetic and all the potential energies for all the particles we have. And again, we generally don't know a specific value, but we're interested in the change. How can we change the internal energy? Two ways. We can change the internal energy through Q and W. Q is heat, W is work. Looking at the heat first. So our symbol for heat is Q. When Q is positive, we describe that as being endothermic. Heat is going into the system from the surroundings. When Q is negative, we call that exothermic. Heat is going into the surroundings. It's leaving the system and going into the surroundings. An explosion, kaboom, this is going to be exothermic. Heat is going to be leaving the system, the balloon, and going into the surroundings. W, that's our symbol for work. The work that we're going to be interested in this class is called pressure volume work, or PV work. If we look at our sign conventions, they match the same sign conventions that we had for heat. When the work is positive, work is going into the system. When work is negative, work is going into the surroundings. We don't apply the terms endothermic and exothermic for work. Those just involve heat. Now, a key thing to look for is whether we have a volume change. When we have a volume change for the system, that's a clue to us that work's being done. If the volume of the system is becoming smaller, if it's getting squished smaller, then we would say that the work is positive. Work is being done in order to squish the system smaller. If the system increases, now the system is doing work on the surroundings. It's pressing against the surroundings and moving them farther apart. So looking for a volume change, key thing to look for when we're assigning work. And that's why we have many times in this chapter scenarios involving a piston. A reaction in a piston can lead to a volume change. And if it leads to a volume change, that means we have PV work taking place. To illustrate this for us, aspects of heat and work, let's add some particles first of all to our container. The particles are in motion, and that motion is being measured by the thermometer that's at the top of the chamber. We can change the internal energy by adding heat. Increasing heat, increasing particle motion, and notice how the thermometer went up. The temperature increased. We can remove heat from the system. Particle motion goes down, the thermometer goes down. That was changing the internal energy due to heat. But look at this, I'm not going to touch the heat gauge at all. I'm just going to change the volume. And the thermometer went up. The particle motion increased, not due to heat at all, but due to work. Heat and work are the two different ways that we can change the internal energy. Here's an application for you. It says, if we define the system as the reactants and products, what is the sign of work in this process? Is it going to be positive or negative? So within this case, we're adding some zinc solid to this container. The container holds hydrochloric acid. If we look at the reaction that takes place, this is the reaction back from chapter 4. This would be a redox reaction where I see zinc solid becoming zinc 2+. I see H+ cations becoming hydrogen gas. Because we have hydrogen gas being generated, in this particular chamber, there's a potential for the volume to change because it's being outfitted with a piston here at the top. So this is another opportunity to share ideas. Check in with the person next to you. If we're defining the system as a reactants and products, what's going to be the sign of work in this scenario? Key thing that I'm looking for here is how did the volume change? If this is my particular system, the piston moved outward as gas was generated. It moved outward, so the volume of the system is increasing. When the volume of the system increases, it is doing work on the surroundings. The system did pressure volume work as the volume increased. The work has a negative sign because the volume of the system expanded. So we've covered a lot of ground so far. We've looked at the relationship between the internal energy and how that is describing all the potential energy and kinetic energy for all the particles. We saw that we can change the internal energy two different ways, due to heat and work. If we look at the sign conventions, when Q was positive, we said that was endothermic. It involved the transfer of heat to the system from the surroundings. When it's negative, we call that exothermic, transfer of heat from the system into the surroundings. Those are summarized here in table 5.1. We want to know all of that information and the corresponding symbols and sign conventions. Let's see if we can apply it. So here we have hydrogen gas and oxygen gas in a balloon. That's the system. A candle is being brought to it at the end of that stick and kaboom, big explosion. The reaction is shown here below. So work on this one. Check with the person next to you. Assign Q and W for this scenario. So I look at this, an explosion, I'm thinking exothermic, kaboom. The Q would be negative as we have heat leaving the system, going into the surroundings. The volume of the balloon, it also increased during the explosion as the particles moved outward. So if the volume increased enough so it ruptured the balloon, then the work is negative. So in this case, Q is negative and the work is negative. Take a second, rank these in terms of internal energy. So we have the particles of matter at different temperatures, showing different states of matter. Which has the lowest internal energy? Which has the highest? So I would rank the solid below the liquid, below the gas. This has the lowest potential energy. This has the highest potential energy. And if I were to look at the temperature, the thermometer is going up as well. So the gas at the top here, highest internal energy. The solid, the lowest internal energy. Now, we could change these after all. We could add heat and take it from being a solid up to a gas. We could have heat removed and take it from being a gas down to a liquid. So if we were to think about those, adding the heat, that would be an endothermic process. The sign of Q would be positive as I add heat to take it from a solid to a gas. If I remove heat from the system, that's exothermic. The sign for that would be negative. So I could raise the internal energy as I go from a solid to a gas, and then I could have the internal energy decrease as I go from a gas to a liquid. Is there any way to get the internal energy for this missing step right here? Well, if I knew how much I added, and then I knew how much left, the difference between those, I could use that to find the missing step here. I can do that because internal energy is what's called a state function. Important term for us. For a state function, the pathway does not matter. All we are interested in are the initial values and the final values. So if I knew the initial value here for the solid going to the gas, and then I saw during my process coming back, I could get then the missing step, okay? If all I'm interested in is the final minus initial, and that can be used to determine the value I'm interested in, that's called a state function. So it turns out internal energy is a state function for us. The pathway doesn't matter. We just need to know the final and initial values. Now, if I were to look at the different parts right here, I think the solid has the lowest internal energy, the gas the highest. Now, if I were to change that, I could also think about this in terms of what's called the enthalpy. They're not exactly the same, but in terms of conceptual trying to rank them, I once again would have the same, solid being the lowest enthalpy value, gas the highest. So what is enthalpy? We often conduct experiments in the lab where the only work that we're interested in is pressure volume work, and that when that takes place, the pressure is constant. If we think about a beaker that's sitting on a Bunsen burner, the beaker, if it's open to the air, the pressure that's exerted on top is atmospheric pressure. That doesn't change during the experiment. So the pressure that we have involved is going to be constant. And the type of work that we would have that could take place is pressure volume work. This condition of constant pressure, sometimes you'll see the symbol then Q for heat sub P, where the P is telling us constant pressure. So the heat that's being gained or lost under conditions of constant pressure might get that symbol Q sub P. That it's also called the enthalpy. The change that we have of heat being added or removed under conditions of constant pressure, that's called the enthalpy. So when we think about an enthalpy change, it's the heat that's being added or removed under these set conditions. Now, what's beautiful about enthalpy is it's a state function. So the rest of the chapter, we're really looking at quite a few different applications involving heat being added or removed, where we can think about that under conditions of constant pressure. That is called the enthalpy, and it's beautiful because it's going to be a state function. So we're interested in its change by considering its final minus initial states. The terms endothermic and exothermic, those also apply for enthalpy changes. The rest of the chapter, we're going to be very interested in enthalpy changes. So at the start of class here, what we've been exploring would be aspects of kinetic energy, especially thinking about potential energy and how it pertains to matter and bonds. For the first law of thermodynamics, quite a few different terms that we want to be clear with, things like system surroundings, heat, work, and the corresponding sign conventions. And we've now introduced the topic of enthalpy. Beginning next class, we're going to take enthalpy and connect it to aspects of chemical reactions and look at other aspects of it throughout the chapter.